For this next example, we're going to need to graph y equals x squared, which we should know how to do, and y equals 2x minus x squared. That might require a little bit of reminding. So let's do a little bit of algebra to help us graph this function. Okay, so y equals 2x minus x squared. We can write it in vertex form. We want to write it in y equals a times x minus h squared plus k, where h comma k is the vertex. And that'll make it pretty easy to graph. So we have, I'm going to factor out the coefficient of the x squared term, which is just -1. So we have negative the quantity x squared minus 2x. I'm going to leave a blank there because what we're going to do is we're going to complete the square. So to complete the square, we look at the x term, take its coefficient, half of it, which would be -1, and then we square that, and we add that in here. Now, I just added a +1 here, but because this minus sign is going to be distributed to each of these terms, in theory, what I really added was a -1. So I need to compensate for that. In order for it to still be the same function, I have to compensate for adding the -1 by adding a +1. And what that will do is it will allow us to factor what's in the parentheses here, because this is a perfect square trinomial now. And so we have that y equals negative x minus 1 quantity squared plus 1, which means it's a standard parabola, except it's shifted to the right one. It's reflected across the x-axis, so it's opening down, and then it's shifted up 1. So if I take my standard parabola, well, we can actually graph the first parabola now. So here's our original parabola. Let's just graph that one first. And then we'll use that to consider how can we graph this using transformations. All right, so here's our standard parabola. I'm gonna shift it to the right one, so it'll be something like that. And then I'm gonna reflect it across the x-axis, so it'll be something like this. And then I'm gonna take that and shift it up 1. All right, let's see what that will look like. So shifted to the right, reflected, and then up 1. So I should have something like this. Again, the area that they're asking us to calculate is pretty small in this picture, so I'm gonna cut a piece out and zoom in on it, like so. What we have then is the area they want us to calculate is right here. It's usually pretty hard to tell just by looking at equations which one is going to be the top function, which one's going to be the bottom function. This is why the graph is always so helpful. So I'm going to move this helpful graph over here. We should notice from looking at the graph, even though they didn't tell us the bounds of integration, we can see that the area is going to start at x equals 0 and end at x equals 1. So when we set up our integral, we're going to integrate from 0 to 1. And then we have to recognize this is the top function, and our bottom function is the x squared. So I have integral of 2x minus x squared which is the top function, minus x squared. And we're integrating that with respect to x. If I do a little simplifying before I calculate my integral, I'm going to have 2x minus 2x squared dx. If I take antiderivatives, what I will get is x squared minus 2/3 x cubed, and we're evaluating that from 0 to 1. And now whatever happens here, we should always expect the answer to be positive. Even if what's over here, this region here, even if that were below the x-axis, we still would expect a positive answer because we want to calculate the area between the two curves. So having this top function minus bottom function thing allows us to be able to do that. Okay, so anyway, proceeding with the calculation, I have 1 squared minus 2/3 times 1 cubed, and then the rest is going to be just 0. It's all going to amount to just 0. And that gives us 1 minus 2/3, which is 1/3.